Welcome back. Now we're going to talk about graphing polar equations in the xy plane. And when we do this, there are two things for us to consider, symmetry and slope. So testing symmetry for polar equations is a little bit different than when we do it for a Cartesian equation. Essentially, we're going to be checking what happens when we plug in r as well as theta. We have to check both of them into the equation and looking at them positive and negative and seeing what the output is. So the definition is similar but different to what you may have learned before. If you are testing r's and thetas, and you can change the theta to negative and it would still give you the same equation that you originally started with, that would tell you that you would have symmetry across the x-axis. Okay, so you could fold it across. You could change that point. If you plug it in and you get a negative r and a negative theta, gives you the same graph as the original equation, that would be symmetry across the y-axis. And if you can have a negative r, positive theta, and that gives you the same as the original graph, that is rotational symmetry about the origin. Okay, so we'll talk about that when we get to the example, but essentially you have to say, well, what happens when I plug in a negative r or a negative theta, and will it still give me the exact same equation? And you have to think about that considering all of the possibilities. So the other thing I mentioned that we need to talk about is slope. We have a formula for the slope of a polar curve, r in terms of theta, in terms of x and y. So if you have a polar graph and you want to find the slope of the Cartesian graph, you can use this formula. F prime of theta times sine plus f of theta, the original function, times cosine, divided by the quantity f prime, the derivative of the function, times cosine theta, minus the function times sine theta. All right, and that works as long as the derivative of x with respect to theta is not equal to 0 at any point. So let's do an example. For this example, let's graph r equals 1 minus cosine theta. First thing we might want to think about when we're creating this graph, especially if we're trying to do it by hand, would be to check the symmetry. And so when we think about checking symmetry, we want to think, well, can I negate the r value and still get the same equation, or can I negate theta? All right, so in this situation, say I only negate theta, that equation would be r equals 1 minus cosine of negative theta. Now remember, cosine of theta, cosine is an even function, and we know that cosine of negative theta equals cosine theta. So this expression would still be the same. R equals 1 minus cosine of theta. So if I negate theta, I still have, this simplifies to my original equation. Negating r won't work. So the only situation I have here is that since r negative theta is on the graph, we know we have symmetry across the x-axis. So with symmetry across the x-axis, we know that we only need to look at values from 0 to pi as opposed to 0 to 2 pi, half of a rotation. So my second step here will be consider values of r for theta between 0 and pi. And so making a table of values works fine to suit our needs here. You can choose as many thetas as you want to plug in. I'm just going to choose 5. We have 0, pi over 3, pi over 2, 2 pi over 3, and pi. And if I evaluate those in my original equation, which is r equals 1 minus cosine theta, I get outputs of 0, 1/2, 1, 3/2, and 2. So I have a Cartesian plane here, not a polar graph. It's a Cartesian plane, XY grid. And if I were to plot these points, 0, 0, pi over 3 would be at a 60-degree angle, about up like this. And at pi over 3, we are up 1/2. So pi over 3, somewhere about there, we're up about 1/2. At pi over 2, which would be 90, we're at 1. At 2 pi over 3, we're at 1.5, or 3/2. So 2 pi over 3, again, we're kind of up at a 60-degree angle, and we're at 1.5. All right, so thinking about that, I'm going to make my point for this, 1.5 up at about 60 degrees here. And the last one we have would be pi, and at pi we are at 2. So you kind of can see, and determining, however many points you choose, you get a curve that looks roughly like this. I'm going to pause and make it look a little prettier, but obviously I could choose far more theta values to give me more points on my graph. So looking at this in a kind of a smoother manner, and it's not perfect here again because I'm drawing this by hand, but we get a curve that looks roughly like this. And because we know it is symmetric across the x-axis, we know that it's going to continue and mirror itself on the bottom. So this is the graph of what we would call a cardioid, all right? And a cardioid is called that because it roughly has the shape of a heart. All right, and so there, you can have different shaped cardioid graphs, but this here is the graph of a cardioid. And that's one way we can go about doing it. Of course, you guys have TI graphing calculators. You can plug that right in to your y equals if you just change your calculator to polar mode.